Hi everyone, welcome to my talk on program generation and verification approach applied to a recent cryptographic primitive called Number-Theoretic Transform or NTT. Multi-stage programming languages or systems such as Meta or Camel or Scala LMS have made a great progress on high-performance code generation from high-level descriptions. However, in terms of reliability of the generated code, these systems provide only basic guarantees such as type safety. We believe that for safety-critical domains, some assurances for more advanced safety properties or even functional correctness of the generated code should be provided. In particular, we have applications in cryptography in mind. As far as we know, program correctness in the context of generative programming is a relatively unexplored topic, and this work aims to provide one approach to address this problem. In this work, we focus on an FFT-like algorithm called Number-Theoretic Transform, or NTT. NTT is often used to accelerate multiplication of polynomials with finite field coefficients. Polynomial multiplication is in turn heavily used in recent cryptographic constructions based on the hardness of so-called the ring learning with errors problem, which is one of the most promising hardness assumptions for post-quantum cryptography. Since NTT is a key building block for the post-quantum era, there has been a significant body of work on an efficient implementation of NTT from the cryptography community. And we believe that the programming language community can do better, not only in terms of performance, but also correctness of the implementation. For performance reasons, most existing implementations by expert cryptographers rely on handwritten assembly. To offer an alternative, our previous work proposed a program generation approach to NTT implementation. Our DSL is based on the tagless final style, and the modularity in our implementation enables program construction that will be very difficult in assembly-based implementations. And performance of the generated code is highly competitive with the expert-written assembly implementation called New Hope, which is one of the fastest implementations publicly available. Correctness of the NTT implementations are usually not discussed in the cryptography literature, but we believe that thorough verification is needed given the importance of NTT for future cryptography. Optimized NTT implementations use various low-level tricks to maximize performance. Low-level optimizations make a program harder to reason about and more prone to subtle numerical errors such as integer overflow. These concerns make verification of optimized NTT implementations non-trivial. This work is motivated by our success in a DSL-based NTT program generation, and we started this work with the hypothesis that the same approach should be a good fit for verification as well. So we propose a unified approach to generate and verify an NTT implementation. We call it unified in the sense that code generation and verification are based on the same DSL program. To the best of our knowledge, this is the first work showing functional correctness of an optimized NTT implementation. In addition, we demonstrate that our program analysis is more precise than pharmacy static analyzer applied to the generated code. The precise analysis results also helped us discover a new opportunity to optimize the performance of the generated code further. The key takeaway from our work is that a DSL approach based on the tagless final style naturally leads to a decomposition of the original verification problem into smaller pieces, which can be separately verified by procedures of appropriate levels of abstraction. Before we get into the technical contribution from this work, we give brief background on NTT and our program generation approach. NTT is a fast algorithm to compute discrete Fourier transform, or DFT, on a finite field. In this work, the finite field is a field of integers modulo a prime q, and DFT computes a certain linear transformation, whose matrix consists of powers of a constant omega n. Since the linear transformation is defined in terms of modular arithmetic, An actual implementation would apply an explicit modular reduction step after addition and multiplication. Entity is an algorithm that computes DFT in O of n log n time. Here, we show the pseudocode of our entity algorithm and visualization of the data flow. The algorithm proceeds in stages ranging from 1 to log n. We note that the algorithm is essentially the same as a typical textbook description of an iterative FFT algorithm, except for the use of modular reduction steps in the innermost loop. In the actual low-level implementation of this algorithm, we need to specify more details such as the data type of the input and how exactly we compute modular reduction with the modulus parameter q. These are discussed in the next slide. This is the pseudocode of the innermost loop, whose low-level details are made explicit. First, we need to fix the size of input n and the modulus parameter q. This requirement comes directly from higher-level cryptographic protocols, where the parameters n and q are called security parameters. In our implementation, we use the same set of parameters from one of existing implementations. Namely, n is 1k, and q is this certain prime number that fits in 14-bit. Since the modulus parameter q is a 14-bit number, we get to use unsigned 16-bit integer data type exclusively in our implementation. But we need to be careful not to cause any unsigned 16-bit integer overflow. Next, fixing the security parameters allows us to use specialized algorithms for computing modular reduction. The algorithms we use here are called Barrett reduction and Montgomery multiplication. Both reduction algorithms are implemented in very tricky ways, involving careful bit-level reasoning. See section 3 of our paper for more details. Finally, since modular reduction is an expensive operation, we want to avoid them as much as possible. Modular reduction has to be applied before we end up with 16-bit integer overflow. The pseudocode here applies Barrett reduction after addition once per 2 stages. We call this optimization lazy reduction. Our DSL is a C-like language embedded in OCaml following the tagless final style. This is how the innermost loop of entity looks like in our DSL. To allow for multiple interpretations of this program for program generation, analysis, and verification, our program is abstracted in 2 ways. The first is the semantics of the DSL construct, for example, what exactly this DSL for loop does. And the second one is the abstraction of the domain where arithmetic operations such as addition and multiplication are associated with. The language semantics is abstracted as an ML module signature following the tagless final style. The concrete semantics is specified by the type expra. For example, by making the type A expra be the type A itself, and implementing the DSL for loop as an OCaml for loop, we can directly execute the DSL program as a normal OCaml program. This simple trick is the basis of our program analysis and verification approach we describe later. Another way to interpret the DSL construct is program generation. By translating DSL for loop to the string representation of C language for loop, for example, we can generate an equivalent C program from a DSL program. The domain of arithmetic operation is abstracted as another module signature. Examples that are relevant for this work include the domain of integers modulo f prime q and the domain of intervals on integers. Coming back to our DSL program, by combining different implementations of the 2 abstractions we just introduced, we aim to realize program generation and verification as non-standard interpretations of the abstract DSL program. The focus of our previous work was generation of efficient vectorized program. And in this work, we want to first verify the absence of integer overflow by interval analysis. And second, We execute this program on symbolic inputs to obtain symbolic representation of entity outputs, which we will use to establish the equivalence against DFT. We now proceed to discuss interval analysis on entity. Our implementation of modular arithmetic has specific conditions on the bounds of input and output values to guarantee the absence of overflow. We developed our own analyzer to show that all such conditions are satisfied. Although the analysis itself is very simple, we have two interesting observations from this work. First, implementing our own analysis is very easy in a DSO-based approach like ours, and it is also effective in the sense that a custom implementation makes it possible to exploit domain-specific knowledge in the analysis. Second, thanks to the analysis, we were able to discover a new opportunity to improve the performance of the generated code further. We will expound on these points in the next few slides. Thanks to the two abstractions we introduced, it is straightforward to realize interval analysis in what was originally a program generation framework. In particular, the domain implementation we use here represents arithmetic operations on intervals on integer modulo q. The only non-trivial question is how we lift modular reduction algorithms to intervals. In particular, an implementation of Barrett reduction on interval is not straightforward, as we will see next. Barrett reduction computes x mod q by subtracting from x the largest multiple of q less than x. To avoid storing an intermediate 32-bit product, multiplication on 16-bit numbers are done by what's called half-product instruction, mal-low and mal-high, which compute either lower or upper 16-bit half of the 32-bit product. We claim that these operations implement Barrett reduction correctly, but for that, x must be greater than or equal to the output of mal-low. However, since mal-low can return any integer between 0 and the maximum unsigned 16-bit integers, if we naively lift mal-high, mal-low, and subtraction to intervals and compose them, we end up with the second argument to the interval subtraction being always larger than the first. So the resulting Barrett reduction on intervals can never compute precise bounds. To work around this situation, we chose a brute force approach. Namely, we apply the integer domain Barrett reduction, shown here, to all integers in a given input interval, and take the minimum and maximum of the reduced result to form an output interval. This is crude, but most importantly, it is as precise as it can get, and in practice, our analysis finishes only in a few seconds. We can also do the same analysis using an off-the-shelf tool such as FLOPS. We found that FLOPS was not able to verify two assertions associated with Barrett reduction. In particular, the first assertion is exactly the constraint on the inputs to the final subtraction. Given our discussion from the previous slide, it is not surprising that FLOPS has trouble with this assertion. In contrast, our custom analysis successfully verified all assertions, thanks to the exploitation of domain-specific knowledge. Our interval analysis also helped us find a new opportunity for performance improvement. Recall that we apply Barrett reduction after addition in once per two stages. Thanks to a precise bound on the input to the Barrett reduction, we found that we can safely skip more Barrett reduction. In our improved implementation, we apply Barrett reduction once in 3 stages. This optimization resulted in a good speedup as shown below. Interestingly, the bounds estimated by FLOPS was not precise enough to guarantee the safety of this optimization. See section 4.3 of the paper for more details. Next, we describe how we show functional correctness of our entity implementation by establishing equivalence against DFT. To recap, the goal is to show that our optimized entity program, whose pseudocode is shown here, computes equivalent results as this DFT formula. One straightforward approach would be to translate this entire entity program into a logical formula in the bit vector theory and verify equivalence of that formula against the corresponding one from DFT. This didn't work because the resulting formula was so large that an SMT solver we used did not terminate after more than 6 hours and before it ran out of memory. The way we verified our entity program is by a decomposition of the verification problem. The problem of verifying functional correctness of an entity program can be naturally decomposed into two parts. One of them is concerned about the low-level aspects of the program, such as absence of integer overflow or correctness of modular reduction implementation. Assuming that the low-level aspect is verified, we want to abstract out the low-level details and separately consider the higher-level question of equivalence of entity and DFT in the domain of a finite field. Since we start with a DSO program where the low-level details around modular reduction is abstracted from the high-level structure of the entity algorithm, it is straightforward to apply this decomposition in practice and separately consider each verification problem. The lower-level aspects are verified via standard methods such as SMT solving or interval analysis. For the high-level aspect, we devise a simple but effective procedure based on the observation that both DFT and NTT compute a certain linear polynomial on their input. Thus, we can reduce the problem of entity and DFT equivalence checking to a much simpler problem of polynomial equivalence. The key step in the decomposition is to abstract out the details of low-level modular arithmetic by removing explicit modular reduction steps from the program. We replace machine-level representation of modular arithmetic in our program with symbolic operations representing arithmetic on a finite field. This gets us really close to the abstract setting where the DFT formula is defined. To make this simplification, we have verified correctness of our implementation of Barrett reduction and Montgomery multiplication using an SMT solver. The symbolic finite field operations from the previous slide are implemented as a new domain shown on the left. Now the input to our entity program is an array of symbolic variables, and if we execute the entity program with this domain, we get a polynomial representation of the entity computation for each output element. An example from the 10th output is shown on the right. For each output polynomial, we check that the extracted coefficients are equivalent to the corresponding row of the DFT matrix. We have confirmed that for all output elements, our procedure succeeded in establishing such equivalence, completing the verification of a highly optimized entity program. Let's recap pros and cons of our approach to program verification in the context of generative programming. Our verification methods relies on programming abstractions such as symbolic computation of polynomials. If we had followed conventional approaches where verification is directly done on a generated program, we need to reconstruct the original high-level structure in a DSL program from scratch. Moreover, since program generation and verification are based on the same DSL program, all low-level properties in the generated program are subject to verification. The downsides of our approach include not verifying the generated code directly and relying on custom verification methods. We acknowledge that these downsides could make our approach less convincing, but we believe that this is a reasonable trade-off between more possibilities for verification and larger trusted base. This concludes our presentation. We described how a modular program generation technique can be retrofitted for verification by showing the first functional correctness verification for an optimized entity implementation. For future work, we are particularly interested in exploring if our approach can be useful for applications outside of entity or cryptography. Thank you.